computer, just in case it can help later. Okay, so let me first show the problem that we are going to solve. We are going to do second. What do you see on my, okay, I believe I know now what you see. So that's good. You can see the problem there, right?
Give me a second. Yeah, I see review the concepts, 3 point. Yeah, I do see that.
Okay.
So 3.1.
Okay, so here, exercises. 3.1, we have, in a population, we have that the mean is 100 and the variance is 43. And we are asked this over here to find this probability of the mean of y being under 101. Do you know how to solve these problems?
Yeah, so I think I did that on the econ lab. So the way that we solved this problem was that, so they've given the sample variance or the population variance of 43, right? And there's
Yes.
n size of 100. So you have to find the difference between that. So the 43 divided by 100, you need that. So let me see what that is. That will give you the one of the variables to solve that. So let me get my Excel out, sorry. So that's 43 divided by, if you ask me about the concept, what it exactly means, I do not know.
Okay.
I just know the steps behind it.
Mm-hmm.
So that probably is the best way I could approach it.
That's okay.
That's 43 over 100 should be 4.
So since you have the problem there, I'm going to actually share a whiteboard and
Okay.
I'm going to try to solve it and explaining how I think about the problem, you know.
That'd be good, yeah.
Which I think is the most important thing of this, to know how to think about it. So I'm going to write first that I have mean, right, of y is 100. And I have the variance of y is equals to 43.
Correct.
So my question is, the first question is, to find the probability, I'm just going to write P for probability, of y bar being less than 101, comma, when the number of observations is 100. So what we need to understand about this is that we are not asking for the probability of y to be under 101. Instead, we are asking for the probability of the mean of y. For the probability of the mean, meaning the average, they don't like to say the average,
right?
But the probability of the mean to be under 101. In other words, this is very different if they ask this question. The probability of y, still capital, being less than 101, this is different. Correct. This is not what we're looking for. So
and I think that they're also, so the output is basically finding the area, right? Where it falls in the bell curve at the end of the day.
Yes, we are going to get there. So I don't know. Okay, here. Yes. So this problem, we can translate it into something else, because we say that when n is large, it approaches the normal probability distribution. So because n is large, I can say that y is, can say like this, and we can practice the notation. Y is normally distributed with mu being 100,
Right.
and the variance, sorry, I meant to say that the variance is 43.
Correct. So this, you're trying to normalize or standardize.
And I'm sorry, I believe this is incorrect because, well, yes, we are saying this, but I don't think we know actually the 100 and the 43, because the 100 and the 43 is actually for y. You see, mu y, not y bar. And this is also the variance of y, not the variance of y bar, as I wrote here. So I erased that there. Do you understand what I correct?
Yeah, but I'm trying to see, why wouldn't you use a mu of y of 100 into the probability of y of less than 101, right? In order to get that base, wouldn't, and
So
I'm not talking about the sample n, right? I'm talking about the mean, the average, or the u of y, which is 100. That is what's needed. That's the population, right? That's the terminology for population. Whereas y bar is the terminology for, I don't think it's population, isn't that?
no, yes, and that is what we need to understand here. That is not the population. So what y bar represent is that you have the population and you have everyone in the population, right? Let's say it's people. So you take a couple of them, right? And for this, you find, let me use another color. So you find for this sample that you took, you find the mean, right?
Yeah.
And let me see. So this is for a sample, and let me do a red to distinguish that we are talking about that sample. Now, mu is for the entire population.
Right.
Like this. I'm trying to also understand something, because I believe that the y bar they are using is for many sample. Okay, yes, so this y bar, right, can be this red one, right? But it could also be something else. I could have to end up with this sample. So my y bar would probably be different, and maybe somebody else come and do something else, maybe did this sample, right? And you see they can overlap, that's okay. And this is the y bar he had, right? And somebody can come and even get closer to the population. That means like getting a larger sample, and his y bar, I expect that is going to be closer to the true value, which is mu y,
Right.
the mean of the population. Is going to be closer than these three, because they have fewer sample. You understand that, right?
Yeah.
So this y bar represents any of these y bar, not just one. It doesn't represent only one thing. It represents any y bar
It could
that
have
we
more
ended
than
up.
one. Yeah, it could have more than one sample.
Yes. So when we plot all these y bar, right, we can make a plot of them. So you can see that y bar itself is a variable, because it's changed every time. The yellow one is different from the blue one, and different from the red. So we say that because y Y is represented by all the black dots, right? Let me show you here. So all these little dots, they represent Y, not Y bar, just Y, each observation, right?
Okay. Okay. Yeah. Yeah.
So because, sorry, so because we say that Y, we assume that Y is normally distributed. This is for Y, each individual observation. Because it is normally distributed, we can assume that also the distribution of the Y bar is going to be normally distributed.
Correct.
And that is why we can use the step we are going to use to solve this, which is using we are going to standardize it.
Yeah.
And from that standardization, then we can find this probability. Okay, so what do we need to standardize it? In order to standardize it, we will say that this over here is equals to the probability of Y bar minus
And
mu of Y divided by
standard deviation.
the standard deviation of Y bar. So here you see from this number, you can get the standard deviation of Y. That means the standard deviation of the observations. But what we need is the standard deviation of the samples of the colorful circles that I have here, right? Which is a different standard deviation. So if I draw this graph here more accurately, it would look something like this. Compared to this one, it would look thinner. Still follows the normal distribution, but it's thinner.
So we're basing that off of the 100, right? Because we have 100. Is that what you're trying to get to?
No, what I'm trying to say is the standard deviation of all the observations
It's 43.
is 43. It's kind of large because we take each one individually, right? So when we plot it here, the standard deviation, you see how it is spread to the left and spread to the right. However, when I work with average of different sample, like the blue one and the Y bar and the Y bar yellow here, right? When I work with those average, they are going to be similar numbers. They're going to be closer together than, for example, you see how, for example, the difference between Y bar yellow and the Y bar, let's say blue, right? Yellow and blue. From here, I'm looking at this sample, right? I expect that to be smaller than the difference of this observation and this observation. So 1 second. This is going to be smaller than yi minus yj. In general, not always, but in general, I expect this to be true. You see what I mean? Because this is already an average. So this is taking multiple observation and dividing by the number of observation, and you get a number, right? So remember, the larger the sample, the closer it is to 100. Mm-hmm. So the sample for this one, you can say that is 1 because you only took one observation. So it is farther away than 100. However, this one gets closer and closer, and they get closer to each other too. So the difference is smaller. So that's why you see that the observation in the distribution, they are closer together because they are kind of like an average. So they are closer together. However, each observation individually, they are more spread. because you don't take an average. You expect an average
Yeah.
to have a smaller error, right? Than when you compare each one individually. For example, this Y1 can be 200, and this one could have been 50, right?
Spread out, yeah.
You take them individually, but when you do an average, here you could have 200 plus 50 plus many other number, right? And then you divide by that number,
Right.
whatever that n is, right? N1. And then you do the same for this. The number, the addition might be similar, you know? So they are supposed to be closer, this average, right? That's why the standard deviation here is kind of close together. This is, maybe you don't need to understand this to solve the problem, but if you want to understand what is going on, then you want to understand this, you know? That's why,
No, it helps. It
yeah,
helps.
and the professor draw it like this in class. Let's see, right? The standard deviation of the, sorry, let me erase that. He drew one on top of the other to show that when you take the average of multiple samples, that's what we're doing with these colorful groups here, right? When you take the average, it's gonna get closer. The values you get are gonna get closer,
I remember that,
packed together. They get packed together because they try to get close to mu of y, this point here, right? They try to get close to this point, so the distribution get peaked, right?
Right.
Yeah.
So the 43 is not our standard deviation. That's a variance. That's for every single.
Right. That's for exactly. That's what you need to understand.
Yeah.
It is for each individual. If you don't look at the sample, if you don't look at all these colorful things, right? Then the variance for all this is for the individual observations, right? Now, what we want to find is the variance between these 4 samples. Let's say it's only 4 samples, right? So we want to find the variance between these 4 samples. And we understand that it's going to be smaller because now we're comparing values that are closer together than when we compare individual values. Because look at this observation, very far from this one, right? Yeah. But when you take sample, they take many observations and compare to many observations. So it's going to kind of get more similar as the sample becomes larger. If the sample is larger, then the comparison is going to be more similar. The similarity is going to be greater, right? So that explains this over here. Okay, and then what happens is if you end up taking the whole population to do a final thought, is if you end up doing a test of the whole population, then what you get is this value here. So what you get is kind of like this. That's how I think about it, you know, because
What, are you
now
drawing something? Sorry. Oh yeah, I see that now. Okay.
Now right.
Cute.
And you don't get that. It's a mistake to think that you get this distribution. The way we should think about it is that we get this value. If we take the whole population, then we get this value because we took all the numbers and we know that it's 100. So if we test the entire population, then we're gonna get mu of y. You see that?
Yeah.
Because it's not a sample anymore. Now it's the population and we know it is 100. Okay. Let's now go back to solve the problem.
Yeah, that's good. That helps.
Yeah. Okay, I don't think we need for this. I'm going to leave it there. So this, now that we know that we are in normal distribution, we say y, you already know what this y is. It represents any sample that anyone could pick, minus the true value divided by the standard deviation of y bar. So now we know that this is not the same as, sorry,
Yeah,
let me change the
variance.
color. Yeah, you don't get it from that variance, right? Because we know that the standard deviation of y is equals to the square root of 43. This we know, yes?
Yep.
But we need to find the standard deviation of y bar, which is going to, and let's find the variance first. The variance of y bar is related by the formula that we saw that I asked part, right? Y bar square.
Oh, by n, right?
Yes. So it's going to be equals to this standard deviation, the standard deviation of the observations divided by another standard deviation, the variance,
Right.
divided by the number of observations. So here we get, this is,
I have
okay.
it.
And we call this the standard error, just to compare it that it is from a sample. That's, the standard error of, sorry, no, that's a mistake.
It should be SE, right?
Yes, yes, but this is the variance, right? And what I want to say is that the standard error of y bar, so, is going to be equal to the square root of this, right? Just like the variance, because it is kind of like the variance. It is an estimator for the variance, so we treat it the same way. So the square root of the variance is the standard deviation divided by the square root of n. That makes sense, right? We take the square root of all this. So the square root cancel the square. We don't have square anymore. And then we remain with the square root of n on the bottom. And this is how we find the standard error, which is this over here, the same. We could say also equal like this. So we say this being less than, the value here is 101 minus the mean or the true value of y divided by the standard deviation of y bar. Okay.
Well, so you're not applying so the standard error takes in the consideration of the sample size.
Yes, it takes into consideration the sample size.
Okay. Got it.
And that's how the standard, if I draw this again, right? Let me do it very quick. We have all of this. So there is a relationship between the standard deviation of all these observations and the standard deviation of any sample that you pick. Right? This is the standard deviation of the sample, and this is the standard deviation of the observation. And because this is a sample, I put y bar. Because it has many different observations within it, right? That's why we call it y bar, because it's not only taking one sample, it's taking many. If it's taking only one, then it's only y,
Right.
like this here. So there is a relationship between these two, and that relationship is this.
Okay.
Yeah, you can see it here. Don't think about it don't think about the standard error. Let's keep it a standard deviation, right? The standard deviation. The standard error is like the standard deviation for the samples. They call it the standard error. See, this is what they call kind of like the standard error.
The sample.
Yes, I know that I am not explaining 100% of what the standard error is exactly, but I believe I'm explaining a good idea so that can help.
No,
right?
no, I think I get it from the book. I mean, I pick up bits and pieces, so I'm putting it together. So yeah, because I know standard error is for the sample, right?
And don't, a standard error is for the sample, yes.
Correct. And I guess the way that I'm looking at it is standard deviation. It can be used for population and sample, you know?
Yes, yes, exactly. So the standard error is we are trying to estimate this part over here, right? We're trying to estimate it. So we call it something different because it is not really the standard deviation. We are trying to get the standard deviation.
Right.
So in order to differentiate that we don't have the standard deviation, we are trying to have something similar. So we call it the standard error. But it's pretty much the same when you are solving a problem. It's pretty much. Right. But what you need to be very careful is you need to differentiate the standard deviation of the observations and the standard deviation of the sample.
Say that one more time.
You need to differentiate between the standard deviation of the observations of every little dot here and the standard deviation of a sample. When somebody come and take a few and then they take, let's say, the same as I did earlier, they take another few.
But the standard deviation of a sample and a standard deviation of population is just a reflection of the population, right?
Exactly, yes. We are trying to reflect the population. That's what we are trying to do, yes. But they are different, right? Because first...
It's pick and choosing, right? So you want to have a different type of, out of 100, you're going to pick 10 samples. You're going to be...
Yes, and maybe I pick different 100, right? So you pick 100, I pick 100, we get different values. But then we compare those values. And when we compare, that's what we get that we call the standard error. So it's a comparison between the sample that you have, between the mean of the sample that you have, and the mean of the sample that I have, right? And we say the mean, that's why we have this bar on top. Because we are no longer comparing the observation, like each individual one. We are comparing only the mean now, which is like the average, right?
Right.
So this equation, you have to have it handy. And you need to know when to use it, which I think is clear now from what we spoke about. Now, using this, we can say that in this case, it's going to be equal to my standard deviation of the observations of the population, right, is square root of 3 of 43, right?
Right.
Divided by 100. What number do we get now?
It should be 0.43, I believe.
Sorry, I'm so sorry. I made a mistake here. Let me see.
No, I think you take the variance.
The standard deviation of 43. What I meant to say here is that we also need, not the standard deviation of 43, sorry, the square root of 43, but we also have to take the square root of 100, yes. And that would be square root of 0.43.
Correct.
Can you tell me what that number is?
Yeah,
if you can calculate.
No, square root of 43 is, yeah, here you go, 0.655744.
0.655
744.
7. I think 7 is enough. So now, I don't know if you know how to convert this into something that looks like this. 5, parentheses,
Oh,
101 minus 100 is 1.
right. So I'm calculating that now.
Yes, divided by 0.6557.
Right. So I did the normal distribution. I'm probably going a little bit further, but
Yeah, that's okay. Yeah, so do you use, are you using RStudio?
no, I'm actually using Excel.
Okay. So you can do it in Excel. I'm going to see if I can do it in RStudio.
I don't know. You can do this in RStudio. I guess I'm not familiar with RStudio or Anaconda. So
Do you see my RStudio there?
let me see. No.
No, you see the board, right?
Yeah.
Okay. One over 0.65. Okay, the value I got here is 0.9364.
Yep. Correct.
Okay. I was going to say something, but I think in the next problem it shows. So I'm not going to say it now. I'm going to
Yeah, I
solve
think
next
those are the
problem.
ones that have a little difficulty because not
Yes,
difficulty because you're doing and or on this one, right?
yes. So what's happening here is, and this might help you understand. So we need to know how to interpret this sign here. This is what can make the problem hard for some people, right? Knowing how to treat this over here. Let me do different color. We have to know how this is affecting, you know, the conversion from this step to this step. It is being affected by this sign. So that is because when we have the distribution, sorry, when we have the distribution here, we focus at a point, right? And the point that we try to focus is at this point. 1 second. We're trying to focus on this is the probability distribution, right? We're trying to focus on the probability distribution where this point is, right? Which is basically where this point is in its own distribution, which is different, but follows the normal distribution. So this is equivalent, okay? So we're trying to see where this point is. Let's say this point is anywhere. I don't know if it's negative or positive. I just put it anywhere. I say that it's here, my point of interest. Let's say T is my point of interest, which is this number, okay? Now, I'm trying to see what is the probability that this Y bar, right? This Y bar is less than 101, which is equivalent of this being less than this is equivalent, right? Maybe you're lost now as I explained, but
Yeah,
I believe you're going to get it now. Just give me 1 second.
okay.
So we focus at this point, which is equivalent. I don't know what sign to use to denote something is equivalent, but I'm going to use
I think
equal
it's
sign.
equal signs, but wavy signs.
no, that is like approximately, like close to. But I'm going to say that that is, I'm going to say it like this, is equivalent, okay,
Right.
to my 101. This point that I find in the distribution curve, this line here, is equivalent to the 101, sorry, 101, I meant to type, to write here. It's equivalent to 101, right? So what this means is that to the left and to the right, I have the same probability as the other curve, which may look different, but it's also a standard deviation. And 101, I put a negative because I just try to say that it doesn't matter if it's negative or positive when I'm doing my analysis. But it's equivalent. You see, the probability on this side and this side is the same probability of this side and this side.
Yeah.
That's what we are doing when we say standardizing. It's equivalent. We're just transforming something to something else that we already know more data about. Okay, so here I'm trying to find what is the probability of something being less, and something being less is anything to the left side.
Correct.
So this is my probability here.
So hold on for a second. So looking at problem B, right? So it's probability of 101 less than the y bar, which is less than 103. So if I interpret it, we're looking for a probability or something y greater than 101?
Y greater than 101, but less than
Less than
103.
103.
So that's going to give you something like this. For part B, we're trying to find something, right?
Right in the middle of it.
We have a number here, we have a number here. So Y has to be within this,
That
what's the
range.
probability that Y is here?
Correct.
So we know that we need to find this point of interest, do something with it, find this point of interest, do something with it, and then we can find the probability.
Okay.
Okay, so we're going to jump to that problem now. Before I jump to that problem, I'm going to stop recording and I'm going to do whatever I did here for my homework too, before we go to the next problem.
Okay. If this is taking too much time, design, let me know.
Oh no, I don't mind. I feel good when I try to explain because it develops my understanding. So.
Is your background in math?
What is it?
Is your background in math?
Engineering.
Oh, okay. Gotcha.
Yeah. Some math, but not like pure math. What's your background on?
Finance.
Okay. Yes.
But I mean, I've been out of school for 10 years, so this is.
Yeah, in my case, I've been out for like 6 or 7, no, actually 5, since 2015.
Crazy. Yeah. So this is refreshing. Like I'm getting back to it, but it's just trying to get it a little bit much more difficult to grab onto it.
Mm-hmm. I'm trying to see where do I have my file for this homework. Okay, here. So let me solve this problem quickly here and we go to the next problem. The next problem, I'm going to try to solve it where I do my homework. And if anything, I can jump to the whiteboard if I need to explain something.
So I think you're still recording, but how do you
Oh no, I'm not. Actually, let me see. Yeah, oh no, I am. How do I stop recording?
The way that I'm doing my homework is I'm doing it all in Excel.
Okay, so for the second problem, we want to find the probability of 101 being less than our y bar, and y bar being less than 103. We also have that n in this case is equals to 64.
Correct.
So that's the setup of the problem. So in this case, we need to find the standard deviation of the sample again. That is what I mean is we need to find again what we found before. Sigma of the equation is sigma of y divided by n, and it should be the square root of n. Yes, this is the equation we used before. And in this case,
43 over 64, right?
Yes, so that would be 43. Is it really 43? No, I think it's the square root of, because they don't give you the standard deviation, they give you the variance. So that's something else you need to be, I make the same mistake. That's why I'm mentioning it.
Right.
I make the exact same mistake and then I'm like, why did I get it wrong, right? But in this case, it would be the square root of 43, which is the what is it called?
The square
root of the variance, right?
Right. So the way that I do it, I do 43 over 64, then do the square root of that output.
Yeah, I'm actually doing it in this way just to show you that you do the square root. Imagine they give you, you need to know why you're doing the square root. You're doing the square root of the top part because they are giving you the variance.
Right.
But if they give you the standard deviation, you see here on the equation that you just use the standard deviation divided by the square root of n. So in that case, it would be only the square root of n. Let's say they gave you the standard deviation is 43. In that case,
that's a good point. Yeah.
Yeah. So you need to know what they're giving you and what equation you're using. Okay.
So what you're saying is that if they gave me the standard deviation, just be careful. I got a standard deviate. I got to square root the sample.
Only the n. Yes. The sample size and not the numerator. You don't have to square root the numerator because it is already the standard deviation. But if it is not the standard deviation, if it is the variance, then you need to square root because what you need is the standard deviation according to the formula.
Yeah.
Right?
Yeah.
And here n is 64. So, okay, so the square root of 43 over 64 is whatever number. I don't really.
You do that on the RStudio too, or how do you do it?
I usually do it in a calculator. When I'm doing the problem by hand, I do it by calculator. But when I'm doing it here, sometimes I just feel lazy and I just put it there, and then I do the R part. But before I do R, in this case, I need to. You see here what I told you earlier. This sign tells you how you're going to use the values from the distribution.
Right.
So let me do you want me to do the board to explain it there again?
No, because it's just the greater than equal to. So what I have to do is in my own mind, I have to isolate it, right? Because
Yeah,
I have to draw the 2 points, 101 and 103, and y is my sample. So as y is greater than 101. So the way I have to set the problem like that. So
yeah.
I think I have to set it up like that in my own mindset.
Mhm.
So what I'm getting is 101 minus 100. The other section would be um, 100 minus 103. That's how I said.
Divided by, okay, do you know, let me calculate the square root of this just to use that number. Or that's okay, I'm just gonna look at that. Square root of 43 over
You want the number?
64. That's okay, I just put it like this. Minus 100. So I'm translating the problem now to this. And then I have, but this is practically just setting up the problem. Oof, what am I doing? And here I have 103.
So Diomedes, hold on for a second, all right?
Mm-hmm.
Go to that. So we're looking at your problem, right? So in the middle of it,
Yeah,
y is greater than 100. No, 101. Y is greater than 101. And y is less than 103, right? If it
yes.
was y was greater than 103, would it be 100 minus 103 then?
For that, I would use this, the whiteboard. Let's see. Let's erase everything that's in the whiteboard. Just clear, maybe? Clear all drawings, yes. So what I'm going to do is I'm going to focus here on the distribution, okay? To answer any question that you have. So let's first set up the problem that you want me to do. You want me to say the probability of
Probability of 101
101,
less than
uh-huh,
y bar
yes,
less than, I'm sorry, greater than.
okay, let's do greater than,
That's not the question, but I'm switching it.
I understand,
Greater than 103.
yeah. So I draw the distribution, and then I locate, I say that my mean is here, and I locate 101 and 103. Say 101 is here, and 103 I say is here.
Right.
So let me do it more, little different. Let's say 101 is here, and 103 is here.
Yeah.
So you're telling me that you want y to be greater than 101. So let me use red. You want it to be greater than 101. Okay?
Correct. Yeah.
But at the same time, you also want it to be greater than 103. Yeah?
Yeah.
So for both to be true, it has to be only greater than 103. Then this 101, I don't need it to find my answer. I only need it to be greater than 103. You see that? Because you're telling me you want y bar to be greater than 101 but also to be greater than 103. That is exactly the same as saying you want it to be just greater than 103. That's it. Because both have to be true.
Right, right.
So you would only calculate this area here, the blue one. Yeah.
Yeah.
That's why these problems is good to visualize what we're trying to calculate, and then you don't waste time trying to find right this part here. This is a waste of time because you don't need it.
So if 101 is less than y, right? So let's just look at that for some. So 101 is less than y, my 100. Okay. Then I'm looking everything to the left of 101. Okay. All right.
Yeah, that makes sense.
Yeah.
Okay, so let's go back. Before we go back, let's just see what we are trying to find in this case, the real problem that we have. So in this case, we want it between, because we want it greater than 101, the red, but then we want it smaller than 103. So smaller than 103 is all this.
Yeah.
But the only part that satisfies both conditions is the intersection in this case, right? The green and red, which was the case on the other one. The red and the blue, only the intersection you need because both need to be true. So in this case, I know now that I only need this area here. So now that I know that, I'm just going to focus here. This area I need to calculate. How do I find this area? So it's going to be all the area to the left of 103 minus the area to the left of 101. You see that?
Say that one more time.
Let me say it doing a drawing. So first, I'm going to represent with red. You understood that we only need this area here, right?
Right, the intersect of it, yeah.
Yeah, so you understood that part.
Yeah.
Now, how do I find that? The way to find it is, what happens if I apply the procedure that we did when we find the area to the left, right? We work with this number, 103, and we find the area to the left. That means that we would have all the area from 103 to infinity, right?
Right.
But that's not what we want. What can I do to get rid of the extra area that I have?
You stop at 101. Or you stop at 100.
I cannot stop at 101 and I cannot stop at 100 because remember that when you use Excel or when you use that table, which I don't use, to find the area, it gives you the total area to the left. When you go to Excel and you say, okay, Excel, give me the normal distribution, the cumulative normal distribution at 103, give me the cumulative normal distribution. Excel say, okay, I give you the cumulative, means everything. I give you everything, all this area, and I stop at 103, right? Yeah. So what you need to do is, after you find all this purple area, right? All this purple area, what you need to do is say, okay, I have more than I need. Now let me find this yellow area here, up to 101. And say, the purple area that I find represented by this minus the yellow area that I'm going to find. That will give me my answer here.
Purple minus, okay, okay.
right? All the purple area which start from negative infinity and stop at 103 minus the yellow area that start at negative infinity, because this is what Excel gives you. And then it stop at 101. You're going to find those two areas because, and I'm going to erase everything, because remember that you are able, the tools that you have gives you the area to the left of a point. Let me see. You can always easily, very easily, calculate the area to the left of any point. You pick a point, Excel gives you the area to the left. Okay, so in this case, I pick 103 right here.
Yeah.
Excel gives me all this area, okay? But I have more than I need. That's not what I want. I want only from 101 to 103.
Correct.
So you know how to find the area at 103 to the left, right?
Right. So you 103 to 103 to the left. Yeah, you do the normalized distribution, right? Is that what you're saying?
Yes,
Yeah,
yes.
you get the sigma.
Exactly everything we did on the previous one.
Yeah, so phi. So to get the area between the ones that we want, based on what I read, I think I guess you find the difference between it. Between
Yes.
the three. Is it between the 103 or 101 or 103 and 100? Because you're stopping at the y of that. You're stopping at the average.
I'm trying to stop here at 101, not at 100, because the problem wants me to stop at 101. You see, it wants it to be not smaller than 101.
Okay.
It wants y bar to be bigger than 101. So I don't reach 100. I don't get there. So let's see.
Oh, okay, okay. So that's why we do the difference between 103 and 101.
Yes, because when you find 103, you find all this area, right?
Right.
But now you say, okay, let me find 101 area and subtract it. And when you do that, what happens is all this goes away and only this part stays.
Got it. Okay.
Yeah.
Okay.
So at the end, we are going to end up with something that looks like this. I'm going to leave it out there. Something that looks like this. The area, some number related to 103, right? Minus something else. That represents the whole area minus. Okay, I need to subtract the other area, which is related with the 101. But I need to put some other numbers here. What are those numbers? And for those, you use the formula, right?
Yeah.
You see what I'm trying to say?
Yeah.
So let's find these two now. Let me erase here. So here we have 100. And here we have the square root of 43 over 64. Yep. And then the same here. Minus 100 divided by the square root of 43 over 64. And then you can use Excel to find this number and find this number and do the subtraction. Make sense?
Yeah, sorry, I was on mute. Yeah. So I'm following.
Yeah, please ask me where you have question, and I'm going to try to make it. I'm going to try to make you understand it. You know.
No. So it was just the setting up the 103 to 100. That was the issue that I was having.
Yeah.
Picturing that, but I think.
And then after that, you got it right.
Right.
Okay, so let's find out what this number is so that I can, and I'm not going, the professor doesn't care how we do the homework. So what I'm going to do is a screenshot of this and put it in the file. I'm going to find it now. Okay. Equal. He just cares that we do the homework, that we try to do it.
I didn't know his previous class did hand calculation.
What happened?
No, he was Partha was saying his previous class did hand calculation.
Oh, okay, yeah.
That would have been crucial.
So here I get 0.9999.
987. Oh yeah, 999. Difference of 0.99.
0.8888. So this is equals to
If you get a chance, man,
uh-huh.
after you're done with this, can we focus? Do you mind going with that Bayes formula and the total probability? If you
Yeah, let's do that.
yeah, I think that's where I'm majority of it stuck.
Mm-hmm.
So yeah, if we can help get that understand, that'd be good. Well, let's just finish this one out first, then we can do the other ones.
Mm-hmm. Let's see. Okay, part C, you understand part C? How to do it?
Yeah, it's just a reversal.
Yeah, which is 1 minus that.
But 165 was a new n.
Yeah, gives you a new. Okay, I'm just going to solve this problem.
That's fine.
And before we go to do what you want to do.